Okay, so in this video we'll talk about inverse functions. The learning objectives are to verify inverse functions, determine the domain and range of an inverse function, and restrict the domain of a function to make it one-to-one. Find or evaluate the inverse of a function. Use the graph of a one-to-one function to graph its inverse function on the same axis. Consider the relations represented by the following arrow diagrams. Okay, so here we have the domain, and we have members A1, A2, A3 getting mapped to different outputs, B1 and B2. So A1 goes to B2, A2 goes to B1, and A3 goes to B3. So these are relations. And so we want to talk about the inverse relation of that. And so the inverse relation is nothing more is going backwards. So now it's the domain and range kind of swap. This time, since A1 went to B1, we reversed the arrow, and B1 now goes to A2. B2 went A1 went to B2, so now B2 goes to A1, and likewise B3 will now go to A3 since A3 went to B3 in the previous relation. So that there is what we call the inverse relation. So when you're given some type of way to represent a relation, such as we did with the arrow diagram, you basically are swapping. So for example, interchanging, if it's given as, say, order pairs, then interchanging the first and second order pairs of each order pair in a relation produces the inverse relation. If a relation is defined by an equation, then interchanging the variables produces an equation of the inverse relation. So for example, consider the relation G given by the order pairs 2, 4, -1, 3, -2, 0. Well, then the inverse relation of G equals 4, 2, 3, -1, and then 0, -2. That would be the inverse relation for G. Likewise, if you're given a relation given by an equation such as y equals x squared minus 5x, then the inverse relation or inverse equation here would be x equals y squared minus 5y. All right, consider this next arrow diagram here. We got A1 going to B2, A2 going to B1, A3 going to B3, A4 going to B2. Of course, this is a function. Every member in the domain goes to exactly one member in the range. However, when we reverse the arrows, and here, once again, this should be the range here, and this is the domain, and if we reverse the arrow, B1 goes to A2, B2 goes to A1, and B2 also goes to A4, and B3 goes to A3. Notice we have an issue. The reversing process here does not produce a function, because if you notice, B2 went to A1 and also went to A4. That is not a function because every member of the domain doesn't correspond to exactly one member of the range. So the input of B2 here gives us an output of A1 and A4. So that's not a function. And we want to ensure that when we do this process, we always get a function. So not every function has an inverse function. And so for any one-to-one function, however, if you remember, then we have what's called, for every one-to-one function f, there is a function f inverse that we denote by f inverse. And if a function is one-to-one, we will always have a inverse relation that is also a function, and we denote it by f to the -1. So the notation f to the negative 1 is read f inverse. Like any other function, we can use any variable name as the input for the inverse relation function. So we will write f inverse of x, which is read as f inverse of x. Keep in mind that this does not mean reciprocal. So in other words, f inverse of x is not equal to 1 over f of x. And once again, not all functions have inverse functions. Let me state that again, not all functions have inverses or an inverse relation that is also a function. Okay, just recap some properties of one-to-one functions and inverses. So if a function f is one-to-one, then its inverse is also one-to-one. For some reason that got left off the notes there. The domain of a one-to-one function f is the range of the inverse. In other words, the domain is the range of the f inverse function. The range of a one-to-one function f is the domain of the inverse. So domain and range get swapped. A function that is increasing over its domain or decreasing over its domain is a one-to-one function. Okay, so we will use some of those properties. If for a particular one-to-one function f of pi equals square root of 2 and f of 5 equals 12 pi, what are the corresponding values for the inverse function f inverse of square root of 2 and f inverse of 12 pi? Alright, so we just use this information that we're given here. We have f of pi, which is equal to the square root of 12. Here we have an input of pi and an output of square root of 12, or excuse me, square root of 2. And so remember, that's f. So its inverse function will have, or f of inverse of square root of 2 will have an output of pi, since that was the input relation, right? In other words, pi went to the square root of 12. So we reverse the arrow, and we see now the input would be, we record this way, we have the square root of 2 going to pi. All right, likewise, if we have f of 5 equals 12 pi, this means what? 5 got mapped to 12 pi. So then the inverse relation goes this way. And that means f inverse of 12 pi has to be equal to 5. All right, next example. All right, the graph of a one-to-one function f is given below. Find the values of f inverse of 2 and f inverse of 5. So once again, this is the graph, is not f inverse. This is the graph of f of x. So we have to use this to find the outputs inverse function. All right, so we're looking at f inverse of 2. All right, so we want to know what the output is when x is, or the input is 2. Okay, a little bit, it's backwards thinking here in the sense now our input here is going to be the y value. So we look for our y value of 2 on the y-axis, and then we follow it to the graph. We have a point, and then that's the corresponding point. So we drop down to the x-axis, project there, and we see that we get an x value of 3. So the inverse evaluated at 2, or with an input of 2, gives us an output of 3. Likewise, we have f inverse of 5. So we find the 5 on the y-axis and follow it to the graph. And we get the corresponding point there, and then project down or follow it to the x-axis, and we see we have an output of 4. So we have f inverse of 5 gives us a value of 4. All right, I'm going to add to this question here. I want to know what is the domain and range of both f and f inverse. Okay, so first let's find the domain of f and the domain of and the range of f. So the domain of f, we could see just by the graph, it's going from negative infinity to positive infinity. The range of f, notice it's seems to appear to be constant, always above 1, and seems to head out to positive infinity. So we'll take that to be 1 to infinity. All right, so from the properties of inverses and one-to-one functions that I have above there, that means the domain of f inverse has to be the range of f. So that would be 1 to infinity. And the range of f inverse has to be the domain of f, which is negative infinity to infinity. And so that's how you would do that. If a function f is 1 to 1, then f inverse is the unique function such that each of the following holds. The composition of f inverse of f of x, which is f inverse of f of x, equals x for each x in the domain of f. Likewise, f of f inverse of x is equal to x for each x in the domain of f inverse. This essentially tells us that f inverse is unique. For any function who has an inverse, the inverse is unique. So we're given f of x equal to 5x plus 8, and we're given f of x equal to 5x plus 8, and another function called g of x, and it equals x minus 8 over 5. Show f of x and g of x are inverses. So essentially what that means to do is to take the composite in both ways and show that it will give us x. All right, so first off, f of g of x. This is f of g of x, which is going to equal 5 times g of x plus 8. But what is g of x? G of x is x minus 8 over 5 plus 8. The 5s will cancel, leaving us with x minus 8 plus 8 equals x. So for each input in the domain of g, the output is x. Now we do the same thing but the other direction. So g of f of x. So we would have f of x minus 8 all over 5, but f of x is 5x plus 8, and then we're subtracting off 8 there, divided by 5, so those 8s simplify to give us 5x over 5, which gives us just x. Once again, x is in the domain of f, and it spits out back and gets x again. In other words, what you have is here's an x, and here's your f of x. So it gets sent to the range of f there, and then g undid it and got back x. So it's like inverse operation there, and this for showing these two compositions equals x here tells us that f and g are inverses. All right, next example here. Show f of x equals x squared and g of x equals square root of x are not inverse functions, or at least on their domains. Okay, so once again, we will try to show the compositions of each one equals x and see why it fails. Okay, so we have f of g of x. So this would give us g of x squared, which is just really square root of x squared. Of course, the square root of x squared is just x, and that's for x. X in the domain of f, which we know in this case g, which in this case we know that would be 0 to infinity. Okay, So that worked out pretty fine. That composition gave us x, and that makes sense. But let's see what happens in this direction. So g of f of x. So g of f of x, where we got square root of f of x, which is just really square root of x squared. Well, here's where the issue comes. The square root of x squared, we like to say this would give us just x, but technically the square root is always positive, and we know that x is in the domain of f, and the domain of f is from negative infinity to infinity. So x could be negative, and we know the square root the output of a square root is always positive. So that's not true there. To make it a correct statement or a true statement, we could put the absolute value around x. In fact, technically, anytime you take the square root of something squared, that is the absolute value of a. And the reason for that is because the square root is always positive. So this is not true. This is not equal to x for all x in the domain of f. And it's clear if you think about what f of x looks like in terms of a graph. If you do a quick table of inputs and outputs, so we maybe say -3, -2, -1, 0, 1, 2, and 3. In fact, we call that f of x equal to x squared. Well, f of x equal to x squared, that would give us 9, 4, 1, 0, 1, 4, and 9. And so if we plot these points here, we would have at -3, 9, -2, 4, -1, 1, and then 0, 0, 1, 2, 4, 3, 9, and connect these guys. We could see that clearly while f of x is equal to x squared is not a one-to-one function. Which means it does not have an inverse as a function. However, what you can do to make this composition true so that it satisfies the conditions of an inverse is to restrict the domain. And commonly we tend to do that if we need an inverse function. You'll see that in like a trig class as well, where you need to talk about an inverse, but you know it's not an inverse function. So if we want the square root of x to be the inverse of x squared, we could say take a branch of it. In other words, we could restrict x squared to the domain it will make sense to. So we will exclude the domain and restrict the domain of f of x equal to x squared to just positive numbers. In other words, x greater than 0 and also 0. And now you could see that it's a one-to-one function, and it has an inverse. And what's its inverse? Well, by what we just showed above, that would be square root of x, since then we wouldn't need the absolute value around x, and this would simply be just x because x is greater than or equal to 0. So functions are often, domains are restricted, so they become one-to-one functions, and therefore you could talk about an inverse function. All right, so here we're interested in finding a formula for an inverse. So if a function f is a one-to-one function, so if f is a one-to-one function, a formula for its inverse can generally be found as follows. Step 1, replace f of x with y. Step 2, interchange x and y. Step 3, solve for y. Step 4, replace y with f inverse of x. All right, so in this example, we're actually finding the inverse function for the one-to-one function, f of x equal to 3x minus 3. Give the domain and the range for both f and f inverse. All right, so step 1, replace f of x with y. Step 2, interchange x and y. So we have x equals 2y minus 3. Step 3, solve for y. So I would add 3 on both sides, and then that would give me x plus 3 on the left, 2y on the right. Then I would divide both sides of this equation by 2, which gives me y equals x plus 3 over 2. All right, and then step 4 is replace y with f inverse. So f inverse of x is equal to x plus 3 over 2. All right, next example here. Find the inverse function for the one-to-one function f of x equal to x minus 1 over x plus 3, or excuse me, x plus 2. Also give the domain and range for both f and f inverse. Okay, so let's go ahead and find, let's do this, let's do the domain and range first. Well, actually we can't give the domain and range first, but let's find the formula. All right, so step 1, f of x is y, replace f of x with y. So we have y equals x minus 1 over x plus 2. Step 2, interchange x and y. So we have x equals y minus 1 over y plus 2. And then 3, let's solve for y. Okay, so here basically going to build up a common denominator, which is y plus 2. So the left, I'm going to multiply top and bottom by y plus 2. So we have y plus 2 over y plus 2 equals y minus 1 over y plus 2. And then we forget about the denominators to give us x times y plus 2 over y minus 1. In other words, that's just the same thing as multiplying, but the least common denominator. Now we'll simplify the left-hand side of the equation by distributing the x. So we have xy plus 2x equals y minus 1. All right, and our goal is to solve for y. So I'm going to subtract y on both sides here to get xy minus y plus 2x equals minus 1. I'm going to go ahead and subtract 2x on both sides there to get xy minus y equal to minus 1 minus 2x. And the left side, you can see we have xy minus y, which has a y in common, so we'll go ahead and factor out a y. So I have x minus 1 times y equals minus 1 minus 2x. Now we're solving for y, so I'm going to divide both sides by x minus 1 to get rid of that and isolate y. All right, so then we have y isolated, and it equals negative 1 minus 2x over x minus 1. And so next thing to do is to replace y with f inverse of x. So f inverse is equal to negative 1 minus 2x over x minus 1. Okay, now we were asked to find the domain and range. Okay, so first we know we need to find the domain of f, and we need to find the range of f. The domain of f inverse and the domain of, or not the domain, but the range of f inverse. So the domain of f, we could see it's a rational function or a fraction type of function, and we're worried about dividing by 0. So we can see we have x plus 2 in the bottom of f of x. And so we need to restrict the denominator from being 0, so it's x plus 2. So when is that 0? It's 0 when x is equal to negative 2. So we need to exclude x values, it's basically all real numbers except for negative 2. So then in interval notation, we would have negative infinity to negative 2 union negative 2 to infinity. I'm going to have to just drag this over just a tad there. There we go. But we know from earlier that means the the domain of f is actually the range of f inverse because they're inverses. So we know the range of f inverse is negative infinity to negative 2 union negative 2 to infinity. All right, now we just solved for f inverse of x and then figured out the formula for it, and we can see that it's a fraction function too, which we don't want 0 in the denominator, and its denominator is x minus 1. So when is x minus 1 equal to 0? Well, that happens when x is 1. So then that means the domain of f inverse is from negative infinity to 1 union 1 to infinity. And based on properties of inverses, we know that becomes the range of f. So we have the range of f to be negative infinity to 1 union 1 to infinity. Okay, so that concludes that question. The graph of f inverse is a reflection of the graph of f across the line y equal to x. Stated another way, if a point xy is on the graph of f, then the point yx is on the graph of f inverse. All right, let's do this example here. The graph of a one-to-one function f is given. Use the graph to graph its inverse. All right, so looking at this graph, which is the graph of f, let's identify some points on the graph. And by the way, here is one point here, and another point that we could use would be negative 1, 1, 0, 1, 3, 1, 3, and looks like it's 2, 10. All right, let's keep track on that. I'll just construct a little table here. So x, well, I would just call it just xy. So we have the points negative 2, negative 6, negative 1, 1, 0, 2, 1, 3, and 2, 10. Okay. And so that's for f. That's f there. And so let's create a similar table, except let's swap the order pairs around. So in other words, our xy this time will be the reverse of the points on f. So this gives us negative 6, negative 2, 1, negative 1, 2, 0, 3, 1, and then 10, 2. All right, so let's go ahead and plot those points. So negative 6, negative 2 would go right about there. 1, negative 1, which would be right about there. 2, 0, right about there. 3, 1, right about there. And 10, 2, which goes right about there. And let's see if I can get this right here. It's kind of hard to graph like this. Let's see, let me make sure I got the points right. 3, 1. I think I have one order pair not correct. What did I do here? Yeah, didn't look right. Okay, so I plotted the point 1, negative 1 wrong. The point should be at 1, negative 1, which would be right here. Okay, so now I can see the graph a little bit better. And see if I can get plotted. All right, so it should look something like that. Should look very similar. So my graphing skills are not up to par. So it should resemble a little kind of like an S shape, just like the other guy. All right, and so that's and the part that we know it's reflected, basically a reflection about the line y equal to x. Well, if we graph y equal to x, which is just a line going through the origin with a slope of 1, it looks something like that there. And let me just change that color there so it looks different. Actually make it dotted as well. And that would be the line y equal to x. So you can see it's a reflection about the line y equal to x. In other words, what I mean by that, well, if you draw a perpendicular to the line like here, that distance from that point here, that distance there would be exactly the same distance there. And that's a reflection. So you can imagine just reflecting that point over, and that would be the inverse graph, and vice versa. Okay, so that's it for this video.